All right, quick announcements. Just, it's so strange to give announcements every day of the week rather than a class that meets every 3 days or 2 days, 2 or 3 times a week. It's like, it's the same announcements every day. So we still have an exam on Friday. Hopefully this isn't brand new news to anybody. On Friday, today, we're going to be going over some practice problems of some of the requests that I got over the last couple of days. We'll come back and explore some more new content tomorrow before we take the exam on Friday. I'm hoping that you get homework feedback by the end of the day. I've been messaging our grader about every couple hours, being like, hey, how's it going? So hopefully you get that. If you have any questions about it, though, I would start thinking about what those questions or what material you would like to go over and start coming and seeing me in my office hours to go over some of that content. In case you don't get that level of feedback. I have been getting that from some people, which is great to see. So we're going to start today by going over some basic Turing machine problems, not anything special with Turing machines, just Turing machines. I don't mean to say the problems are basic, but we're using basic Turing machines. And then we're going to be looking at context-free pumping lemma, non-deterministic Turing machines, and then countable and uncountable sets. So I have 2 Turing machine problems, and I think it was 3 countable and uncountables. Otherwise, there's a single problem to try to get this all into 50 minutes, but let's see if we can quickly answer this first Turing machine problem. We're going to remove the first A from a string. Alphabet is AB. And we want to design the transitions such that we remove the first A.
You can remove, like, replace with a blank space or B.
We want to shift everything else over. So we basically want to remove it from the string. And then you're having trouble getting started, my recommendation is to think about what methods, what Turing machine methods you have. And try to kind of write a quick Turing machine level pseudocode for each of those methods. And then convert those into actual transitions. When someone thinks they have an answer, I have a pen for you and a lot of space on the board. Want to come do it?
Sure.
Yeah,
Am I writing with the transitions?
yeah. You can write it in whatever form you like.
Somewhat complex form.
I forgot it. I can go run and grab it real quick. I'll say. Okay, all right, so you're saying we can do this in 4 transition rules. I was gonna have something a little bit more complicated than this, but let's see if this works. So Q0, I think on a B makes the most sense. You switch to Q1 and draw a blank on a B.
And then you go over all the B's till you find an A and replace it with a B. So it would essentially be like taking out the A and pushing all the B's into the
Okay,
spot.
pushing the A into the B's spot.
Yeah. Or a B, the B.
But then you need to write a B as well. Yeah, you remove the A and make a B there.
Yeah.
Interesting. I think that would do it, aside from the resetting it to the left side, but I think that that should work.
Is it supposed to be on the like same
I think-
starting spot?
If the output is to be measured, I think it makes the most sense to do that. Something in the back?
I was thinking that A was first, like, character, but
Yeah, if the A is the first character, then it still replaces it with a blank and goes to the final state and it moves right. So that actually is the one case, I think, where the head is at the first character.
I mean, otherwise you could just walk left until.
Yeah.
you get to the start.
I don't know, it's just missing the case where if it's a string of all B's, if you remove that first B, you should then put it back at the very end.
Oh, I guess.
Yeah,
I had
that's a good point.
one more state.
Yeah, the one special
If you're in
case.
like Q1 and reach the end, just
Yeah, I guess Q1.
add that B
like,
back.
Q1 with the blank, you just write it in.
Yeah. Yep. So one more transition, Q1 on a blank. Doesn't matter which direction we move it. We're not worrying about doing the. I think this is probably as simple as you can get it. Does anyone have any questions about this example, or have they had something dramatically different and they want to check if their idea or solution was correct?
Could you use 2 tapes?
Yeah, for any Turing machine problem, as long as we discussed in class that it's an equivalent type of Turing machine, I can't imagine restricting you to a simple Turing machine or a basic Turing machine. Basically, if we've shown that it's equivalent, then you should be able to use that computational power. So you can use a 2-tape machine, a 2-tape 2-head machine, a multi-dimensional tape machine, whatever you want.
I was gonna say, once you know your string is like good with the A replace, You can just add, you don't have to leave the end there.
Yeah, as long as you have successfully moved it from the left side. If you're trying to move every character over as you go from the right side, then you need to know where it ends. But that is a significantly harder problem. So you can see very much that you can design two different algorithms for this process, one of which is significantly easier than the other. So oftentimes, just like with code, it is best to spend a little bit of time designing or thinking through the solution to think, can I come up with something that's simpler, especially on an exam where there's a time limit? The simpler solution, if you spend 1 minute saving yourself 5 minutes, knowing when to spend that extra time thinking about an extra solution, or when to just get something implemented, if there's not likely to be a simpler solution, that kind of intuition will serve you very well. Questions on this first Turing machine problem? Aside from where's my eraser? Not gonna erase it this way. All right, so there's one more Turing machine problem, but I think I'm gonna come back to it after we do at least one of each type of question. So if you want to start thinking about it, or this is one of the more useful things for you, think about designing a Turing machine that adds 1 to a binary number that is on the input tape. Maybe. But we're going to switch over to the context-free pumping lemma. So we want to show that the language, I can't even see from that low res what this is. We have A to the I, B to the J, C to the I, D to the J, where I and J are greater than or equal to 0. When I show this is not context-free with the context-free pumping lemma. So before we get too into this, what are the major steps of the context-free pumping lemma?
The first thing you need to do is kind of just set the premise of like, you know, U, V, Ti, X through Y, like basically laying out all the tools you're gonna use. It's kind of how I think about it.
Okay. I think that is probably the second step. I think we want to do something like, say, let W equal and pick some kind of string.
Sure.
Pick a string, and then once we pick the string, and then we want to think about what are all the breakdowns, the possible breakdowns of that string. So 2 would be identify call it VXY. And what are the things that we know about VXY or VY, or what are the rules that we know that we need to adhere to?
VXY has to be greater than or equal to 1. Like the length of it.
VY has to be greater than or equal to 1.
Okay.
And the length of the XY has to be what?
Yeah.
And so we'll let W equal something based on M. So we're going to pick some string that has some repetition, some value based on M. And the restriction here is the length of W has to be greater than or equal to M.
With the string, could we use the string like A to the M, B to the M, C to the M, G to the M?
Let's see what happens if we do that. So we're gonna have A to the M, B to the M, C to the M, D to the M. Great. That's a nice intuitive starting point. If you get a little ways into this and find that there are some issues, then you usually start to have a better understanding of what those issues actually are. And then you can circle back to this and pick a better string if it doesn't work. In this case, this will work. What's the intuition that leads you to think that this might work?
I mean, there's nothing that says that they can't be this.
Yes.
So let's say.
So setting them to be the same might be something that's really interesting or would allow you to,
Break the levels somehow.
yes.
Oh.
So we want to set this up with kind of, it has the most fragility to it, where the smallest changes that you make to this string break the language. If we add one A to A to the M, B to the M, C to the M, D to the M, is it in the language? No. If you add one B to it, is it in the language? No. If you add one C to it, is it in the language? No, it's a really fragile state. Which means it's great for the pumping level. Basically, any change you make to this string is in the language, that's an important thing to note. Let W, it needs to be in the language. You're not saying let it be in the language, but you're saying let W be this, and this is in the language. So you just want to be able to say something like, I should probably say something like, W is in the language, we know this. You can't pick a string that is not in the language. All right, so now we have this, what are the cases? A lot of cases, I picked it out on purpose.
Be all of each letter, like all A's or all B's or all C's or all D's.
That's some of them.
Yeah.
And then some A's, some B's, some B's, some C's, some C's, some A's.
Yeah, so we have cases. This is probably too many cases for me to throw on the exam, because you're gonna bog yourself down with identifying each of these cases and showing the same thing for cases. If something like this, where there are singular cases, appears on an exam, I am okay if you group cases together and say similar logic holds for each of these cases. If you explain the difference between the cases, outline a generic state, and then say, this is the part that changes based on which case it is. That will save you a ton of time. So we want to say that BXY is made up of case 1, all A's. Case 2, some A's and some B's. And the rest of the cases, B's, B's and C's, C's, C's and D's, D's. Random grammar note, the apostrophe is only useful if the thing is a single letter. As soon as it's more than one letter, the apostrophe goes away. Random grammar note.
That's kind of.
So is Harley gonna take off like 10 points if we put?
Not relevant to the class, but it's something that I see people mess up all the time. All right, so here's all the cases, but we note that these cases are all very similar. And these cases are all very similar. So we really only need 2 descriptions in two big proof types in this. But do note that this will further break down into more cases, which is kind of annoying. But let's start with the easy one, all A's, all B's, all C's, or all D's. How will we make that argument?
Do anything in a bridge?
Yes, but actually writing it out, like what would the actual language look like? I think that's where a lot of people are stuck on how do you proceed? They understand the basic idea of what breaks it, but what is the language? How do we write that such that it's a good argument?
Maybe, I mean, so I know what you're kind of supposed to write down, where you'd have like, you said for like all C's, correct? Is that what you just?
Yes, all A's, B's, C's, or D's, we're gonna lump them all together.
Sure, but like, so like you'd have A to the M plus V, you know, the length of VXY.
Yeah,
And
yeah,
then-
so we're gonna group case 1, 1, 3, 5, and 7 all together, and then say. Okay, case 1, 3, 5, 7. Now I wanna say. Let I equal 2. This just means that we're gonna do the loop one more time. This also means that Vxy is all A, B, C, or D. So now we can say the form of the string you can complete this argument and basically show that this is case 1, this is case 3, and you'd have a couple others for case 5 and case 7. And then I would myself write, in each of these cases, the pumped string does not adhere or is not in L. Therefore, if this is what's picked for Vxy, the resulting pumped string is not in the language. But to complete this proof, we need logic for each of these cases. So we also need to look at cases 2, 4, and 6. How are we going to handle cases 2, 4, and 6? Yeah.
So this one sucks because, you know, when you're doing some A's and some B's, you should be able to put the XY anywhere in, like, for instance, in the case 2, some A's and some B's, you have to be able to put like VX in like some A's and then, you know, kind of march down the A's and B's.
Yeah. If we have, we'll take case 2, where we have some A's and some B's, and we're going to say that this is the dividing line between the A's and the B's. We know that Vxy is somewhere in here, but we don't know exactly where. We could have it such that V, the thing that is pumped, is all A's, and Y is all B's. We could have it where V is some A's and some B's, and Y is all B's. We could have it where Y is some A's and some B's, and B is all A's. So we need to think about where exactly this is coming from. So we have, you know, B is here and Y is here, B is here and Y is here, B is here and Y is here, where we have some overlap. So we're going to further break this down into these kinds of cases where we don't know where V and Y are exactly. The other thing to note is either V or Y could be length 0. We know the length of Vy has to be greater than or equal to 1, which means something gets pumped. But one thing to note is if one of these is empty, then the other one falls into one of these cases. So you can make that argument. So let's start with V's and Y's are separate. So we can lump these cases together to say that this could represent A's and B's or B's and C's or C's and D's. Regardless of what we want, especially on an exam, if something like this were to show up, please group these together. I'm going to try to give you something that's simpler than this, but if something that's simpler, if this is the simplest thing that I can reasonably come up with, that I know that we've gone over and I know people will be successful or more successful at, then save yourself the time, group them together. So B's are here, Y's are here. Is. In this case, we are pumping both V and Y, but what we don't know is the length of V or the length of Y. It turns out for this to not matter. If we wanted to represent what this looks like now, we would have A to the M plus the length of V, B to the M plus the length of Y, C to the M, D to the M, And now we need some way of saying that this cannot be in the language. What is a reasonable argument that says that a string of this form is not in the language?
Either V or Y have to be at least length 1, so.
Yeah, so you would want to say either V or Y have to be at least length 1. If you compare the number of A's to the number of C's and the number of B's to the number of D's, at least one of these will be at least one more than at least one of these, which means that we're not in the language. Because the number of A's and C's need to be the same, the number of B's and D's need to be the same. We're guaranteed that that's not the case because at least one of V and Y is at least 1, which means when we look at A's minus C's and B's minus D's, one of these is going to be greater than 0. Question?
But I can also be 0 in some cases, right? Which would,
You could set I to 0. So up here I should say, let I equal 2. And you could also make an argument where I equals 0, and then you would have M minus the length of V, or M minus the length of Y, and then you still get the same thing here, that one of these is going to be not 0 when you subtract.
okay, but can't they both be 0 and that would still be in the language though too? Like we have to like argue that.
I and J are greater than or equal to 0.
Like, no, I meant like the I, like for V to the I can equal 0 and then Y
Yes,
I can equal 0.
if one of these are, if one of these are 0, then one of these still breaks. So if you were writing out this argument, let's see, you'd say something like I would make this kind of argument where you basically say the number of A's minus the number of C's must be 0 in order to be in the language. The number of B's minus the number of D's must be 0 in order to be in the language. So if you add to this, and we know that one of V or Y is at least 1, then one of these will break and not be in the language.
I'm a little confused definitionally, because the definition for the context-free pumping level was like V to the I, X, Y to the I.
Yeah,
Implying that V and Y, so they're looped the same amount of times.
right.
Okay, so.
But they don't have to be the same length.
Okay,
You could have whatever V is length 1, whatever Y is length 10. If you pump them both twice, then you end up with something of length 2 and length 20.
yeah, but if you pumped it 0, it would, for in our case, we're saying all A's and, or there's A's and B's in it. Does that not imply that there'll be at least one A and B and one B and Y? Or
Not necessarily.
not necessarily? Okay.
We don't know that for sure. We just know the length of Vy is greater than or equal to 1. Our opponent, if we're thinking about this in terms of the pumping lemma game, they get to pick the VXY however they want, as long as it adheres to these two constraints. They can pick whatever they want. They can say the length of V is 0, and the length of Y is 5. And the length of Y, and Y comes from all B's, or some A's and some B's, or they get to pick that, and it's up to you to show that no matter what they pick, we can break the language with some number of repetitions of V and Y, whatever they happen to pick.
So in an A and B case, you can just have like V is all say A's, X is B, and then Y is just nothing.
Yes,
Okay, that makes sense now.
so we want to make this argument, and then we can tie everything into this argument, where this is this case. Now, we can kind of pair these cases in another similar kind of argument, where if B is between these two things, if it's length 0, then Y is all B's, and we're actually in case 3, and not in this case 2. Because the only thing that we're pumping is B's. But if V is length at least one, and in fact, it would need to be at least two to have some A's and some B's in it, then what is the form of the resulting string?
This case would be, you know, like. A, B, no, that's not right. A, B, B.
Yeah, we're gonna, after we move to this section that's supposed to be a bunch of B's, we're gonna go back and see another A. If we say let I equal 2 and V of length greater than or equal to 2 is going to have at least one A and at least one B, if we repeat that, then we break the form of the language where we have to see all of the A's and then all of the B's and then all of the C's and then all of the D's. So it doesn't matter anymore how long V is or how long Y is. If they're made up of some A's and some B's, we can break the structure of the language with any number of repetitions. Note that the bad case to choose here is I equals 0, because that's going to make your proof harder. If you choose I equals anything of 2 or above, much easier. You just show that the structure is broken.
So that's what I was confused about. So we're allowed to just pick a I and it doesn't have to be 0. We don't have to argue for the case 0 as well.
Correct.
Okay,
As long as it breaks for a single I. So basically, if we were to do this in propositional logic, we'd say something like, for all cases, there exists an I such that I modify W, how do we want to say it? Modify W, W sub M is not in the language. Take you back to the screen.
I think apples free.
So one thing I'm still wondering about is how do you demonstrate that a to the I minus c to the I is going to equal 0 or not equal 0? Like how do you?
So that just comes from the language definition, where we know that the number of A's minus the number of C's, since we have I minus I here, that has to be 0.
Right, I guess
For any value Y, 0.
so I know it has to be. How do I demonstrate that it is?
This is where I don't expect a level of mathematical proof. I can go over how you would do that, but as long as you point out something like the logic of that, then I don't really care how it's communicated, as long as there isn't anything false in your communication, and I can see what you mean.
I think if there's a simpler way to, because logically, you can never pump A and C or B and D together.
Yes.
So do you really need to write out, can I just say that? Because
I wouldn't even need to show it, you just show your cases, and you don't consider those cases. You could, if you wanted to justify it, the way that I would justify it is the length of Vxy has to be less than or equal to M. If we have a string, A to the M, B to the M, C to the M, D to the M, then there's no way to have an A and a C in the same string that's less than or equal to length M. Because
yeah,
there are M B's.
but then, so if A and B is pumped, I mean, it's gonna break. I guess, I just think that this is more complicated than it has to be, because like the two I's are never gonna be together and the two J's are never gonna be together. So they're always going to break.
That is. I see where the logic is coming from. But I don't think that that would work for a generic case or a generic, it doesn't walk through the proof such that it's a logical proof, or it's an intuitive proof rather than a logical proof.
Okay.
And I generally like to just focus on the intuition where possible. The one place that I'm a little bit stingy is on pumping them.
Okay. Because
I think that that's an important kind of proof that we don't really see in discrete. It's an important kind of proof by contradiction that it's useful to know and useful to be able to lay out the proof such that everyone will take it seriously, whether they have formal training or not. So I think this is a good question.
Yeah, I'm still trying to figure out how do you account for the case where you pump A and C or B and D and they just coincidentally have the same amount of A's and C's or B's and D's?
We cannot possibly have those as cases. And the reason is that the length of M has to be, we picked this string, because we picked this string, and the length of VXY has to be less than or equal to M, how long would the string need to be to contain at least one A and at least one C?
I'm not sure.
So we have BMs or MBs, right? We have B to the M, that's length M. So to have an A on the left side of that and a C on the right side of that, what is the length of this string?
So M+2?
M plus two, is that less than or equal to M?
No.
No. So that cannot possibly be chosen. We cannot choose a string with both A's and C's in it. To pump, because the length of what gets pumped. From the beginning of V to the end of Y has to be less than or equal to M characters.
Okay.
This string is not less than or equal to M characters. To get to M characters, we have to get rid of the A and the C. In which case, we're in the case all B's. If we wanted to incorporate this A, we would have to get rid of some B's. In which case, we're in case 2, some A's and some B's. We could get rid of more B's and add more A's on the left side, but we would still be in case 2. There's no way to build an extra case that contains A's and C's, and no way to build a case that contains B's and D's.
Okay.
If we picked a sillier string like this, where we pick A to the M over 2, B to the M over 2, C to the M over 2, D to the M over 2, this proof is way harder now. Because now we can come up with a string that is less than or equal to M that has A's and C's in it. And in fact, the pumping lemma will not be possible if you choose this string. So we really want to add there exists some string in the language such that for all cases, there exists an I such that the modified string is not in the language. So you want to pick an intelligent string so that this all lines up in your proof, which is why the A to the M, B to the M, C to the M, D to the M is excellent. Does it get any easier if you pick A to the 2M, B to the 2M, C to the 2M, D to the 2M? No, it's the same number of cases. What about A to the M squared, B to the M squared, C to the M squared, D to the M squared? Any easier? No. But each of these have to be at least M in order for this proof to be broken down into these exact cases. And that's as easy as it's gonna get. Questions on the outline, on the proof type, how this works? Four hands. Teach me to forget my eraser again.
I brought one for you. On the table.
Oh, I appreciate you. Doesn't even see it, continues to use hands. Nobody said anything until that point. It's right there. Ooh. All right. So hopefully that helps identify how the pumping lemma works. Not everything is going to break down into that many cases, but you just need to make sure that it's thorough, that it includes all of the relevant cases so that you can show for each case, for each type of VXY we could choose, there exists some I that breaks it. All right, non-deterministic Turing machines. Here's a reasonable question I could ask you. Design a non-deterministic Turing machine that recognizes composite numbers written in unary on the tape. Do you remember what composite numbers are? No. Composite numbers are not prime. Anything that is not prime.
Just like. Non-deterministic, could you just go to the end and then like. either validate or not validate, and since it's non-deterministic, one of your outcomes will be the right one.
In what sense? How do you go to the end to validate? You need to know the outcome of this is gonna be the number that divides it into evenly. So we need to be able to identify that number. But non-determinism kind of just lets us pick it. We choose the correct one. But we do this non-deterministically with a Turing machine by basically, there's gonna be a second tape that's gonna include the current divisor. And we're going to split into. Here's where we start. We're gonna say, basically. Mod 2 equals 0. We're gonna have one fork that's going to be checking mod 2 equals 0. And then this is gonna be an internal node. Then we're going to check mod 3 equals 0. And another internal node, and another one that says mod 4 equals 0. And you're gonna continue this process until we have a value here that is the length of the input. Or if we have some way of identifying half the length of the input, or the square root of the length of the input. Any of those will work. And remember that non-determinism, you just identify this. You don't even have to describe the process. You just have to break down into, on one hand, you're going to start this process, and on the other hand, you're going to non-deterministically move here. And just start explaining that. Does this layout make sense to people?
So that's the answer?
Well, we need to define the transitions for it, but this is the idea of how we're going to build the transitions. It's the idea behind the transitions. So we have some Turing machine. On tape 1, it's just going to be unary, the number. And tape 2 is going to contain the current divisor. So it's going to start out as 2, and then it will be 3, and then it will be 4, and then it will be 5, and then it will be 6. And the goal is to see that these numbers evenly divide this number. So on one hand, we're going to have a transition that says Q0 on a 1, when we see a 1, is going to transition to Q1, and we'll just do nothing. And I guess we probably even just want to stay. We can include a stay option. And this is going to be the equivalent of like. We're going to transition to Q1 says does. Does the divisor evenly divide the number? Yes or no? And then. And I guess we need the second tape as well. So Q1, 1, 1. We'll write 1 and 1. Stay and stay. It's fine. On the other hand, we'll have Q0 on a 1 and a 1. That's just going to move right. So we'll go into Q2. And we're going to basically, the goal of Q2 is to add one number to the current divisor. And then reset and answer that question again. Does that concept make sense? So non-determinism doesn't say, this isn't deterministic, this isn't like an algorithm, this is just allowing you to freely fork your program. You can think of the fork when we do this process here, this is breaking this into a second Turing machine. We're kind of cloning this whole system. And making a new thread to answer this question on the new thread.
It's like supposed to be like a recursively enumerable, like.
Kind of, yeah, and then we have non-determinism, we can decide, once the current divisor is the length of the unary tape, we'll be able to reject. And say that there's no divisor into this that works.
So what's the rest I don't think I understand.
Yeah, let's draw out the rest of this. So notice that what makes this non-deterministic is the fact that we have two transitions that start in the same place.
Oh,
So this is what makes it non-deterministic. We're going to be able to basically do both of these simultaneously to figure out what is the appropriate current divisor that's going to go into unary. If I gave this to you on an exam, I'm probably not making you write out the transitions for this. I would probably just have you write the logic. So rather than actually go through, it's going to be way too many transitions to throw on an exam to begin with. There's just too much here. But let's talk about the process. I think the process of identifying non-determinism is more important here. So you would state that you're going to have two transitions that leave the same place. And you need some diagram of like, we have we're going to clone our Turing machine and we're going to make a new current divisor. And we're going to non-deterministically both check the current divisor and produce the next divisor. We're going to do those at the same time. That creates a new process or a new fork of our process where we have a new question for our Turing machine. And we will kind of be running all of this in parallel. And again, I like to go back to the concept of the password for non-determinism, where I could guess a bunch of times about what the first letter of your password is. I would need a bunch of forks of the program of each one of these types in a different password. And eventually one of those processes would identify the correct password. You just have a bunch of them. So rather than one at a time going through that, the question is just, you just happen to choose the right one. And if there exists a way such that this process could generate the correct answer, then we accept. Similarly here, whatever the actual divisor happens to be, we're going to choose to increment the divisor, increment the divisor, increment the divisor until we have something that goes into this number, and then we're going to check it. And it will just work out. Because non-determinism is cool. It's not how we program because we live in a deterministic world. We have to program deterministically. We can't just fork and guess and fork and guess and fork and guess until we happen upon the correct one. We need some deterministic way of parsing that and doing it one at a time. But non-determinism lets us choose the right one.
It's hard to count.
So as an example, we have the unary number 9 on the table. And we would start with a current divisor that is 2. So we would need some process that says, does 2 go into 9? So we would have the transitions that says, does what is on this table go into what is on this table? We would need the transitions that define however many unaries there are here. That's what we're going to do here. Some process that does that. And then we need a separate process that at the same time is going to add 1 to this. After we add 1 to this, we fork the program. And now we say, does this go into this on a separate thread? And the answer is yes. But at the same time that we're answering the question, does this go into this? There's another process that is adding 1 to this and starting the next fork and says, does this go into this? So we can much more quickly and efficiently in a non-deterministic world, figure out if there exists something in here that goes into something here. Whatever happens to be here. Yikes, we're over time. So I'll throw these slides up as soon as I get back to my office. There are a couple of countable and uncountable set examples as well. We can go over these at the start of tomorrow's class as well. Being the same. You can have access to chat, if the square root of that goes into that, but that's gonna be way more complicated to actually write the Turing machine program for. But yeah, you would eventually be able to turn out.
Find it. One that fits in just to simplify.
If the
Well, and it's probably gonna be more of an idea. So really good non-deterministic area, example, I only have a few sensations.
Yeah.
Because I wouldn't want to use the question that's gonna take me more than 10 minutes to answer.
Think of just case where you get.
Yeah.
Prime.
I know. But I don't have to- I think.
This depends on the company is really easy to do. That's something I also.
This
keep in mind.
doesn't have to have necessarily, I guess, it's like, it's not going on.
On an example, think about it, people generate quickly and make something that is possible within 10 minutes.
Yeah.
So I had a question about that. And at least being able to time this, I don't think writing the transitions for a non-deterministic Turing machine is as important. It's easier to generate something like, here's a regular Turing machine, show me you understand the transition. Here's a non-deterministic Turing machine, show me you understand non-determinism. And how that's.
So, yeah, I think my answer was mainly overcomplicated because I wasn't sure on some assumptions I could make, because I didn't know
How things are.
they non-zero to accepting something that wasn't in it. So it's really no sauce.
On some number
What
equals.
is it stays, and it might have
It's not, it's the number itself, we accept,
Yeah.
and we were done, we're good to go, so.